Hi Saints, this is Mr. Matthew Lim. Today I will be delivering the second lecture on gravitational field. We will revisit objectives C and E and cover a new objective J. Without further ado, let's look at the first concept. Effect of Earth's rotation on the value of acceleration of free fall. Right, look at number one. Now, there are actually two cases here. A body at the pole and a body at the equator. Now, a body at the pole actually rotates on the same spot, all right, as the Earth rotates. However, a body at the equator actually moves in a circle. And because of that, part of the gravitational field strength is needed to provide the centripetal acceleration. Let me highlight this. Okay, this is the important part. But at the pole, there is no centripetal acceleration. That's because the body is merely rotating on the same spot. Without going into greater details now, let's look at the magnitude of the centripetal acceleration. If you use the formula omega r squared, where omega is actually 2 pi divided by the period t, right? So if you substitute the values into the equation, you get a very small value for centripetal acceleration. So a body at the equator experiences a small centripetal acceleration. So now we are going to study the effects of Earth rotation on the value of acceleration of free fall. So we are going to go straight to work example 5, all right? Let's go straight to work example 5. Now, if you look at this example, I'm going to go to this diagram. You'll notice that a person at a pole actually experiences two forces, one his own weight, mg, okay, mg, next the normal reaction, n, okay. So the person is actually rotating on the same spot. So we will write mg equals to n, where mg is the true weight, n is the apparent weight. So you have to learn this. This is an important point. Apparent weight is actually the normal reaction experiences by the person. So true weight equals to apparent weight, and you can equate this to, okay, let me erase this. I can equate this to mg prime, right? So the true acceleration of free fall is equal to the apparent acceleration of free fall. So at the pole, the person actually experiences the true weight, okay? So that this is the true weight. This is the true weight of the person. Right. The person at the equator, look at the green man, also experiences two forces. This is the true weight, mg, okay? And then the apparent weight, I call this n prime. So this is the apparent weight. So what's the difference between the first case and this second case? For this second case, because the person is going in a circle, so there must be a net force towards the center of the circle. So this net force is equal to MAC, right? Mass times centripetal acceleration. So the net force is given by the true weight minus the apparent weight equals to m r omega square. Okay, r omega square, or you can just simply call it AC. So let me write again, mg minus mg prime equals to MAC. Right? So if I cancel the m away, then you notice that the apparent G is actually equals to the true G minus AC. Okay, so let's look at this side. So we have this. apparent G equals to true G minus AC. So the person at the equator actually experiences smaller weight. So I'll write W at the equator is equals to mg prime, where g prime is actually smaller than the true G. Okay, so why the person at the pole experiences the true weight? Well, we can see very clearly now, as you move from the equator to the pole, actually the circle getting smaller and smaller. So I'm going to draw the circle here. Can you see this is the circle of rotation? Let me draw another one. As you go closer to the pole, the radius of rotation becomes smaller and smaller until eventually at the pole, the radius is 0. At the pole, the radius is 0. Okay? Remember, this centripetal acceleration AC is equal to R omega square. As we move from equator to the pole, R becomes smaller and smaller. R decreases until eventually R becomes 0 at the pole. So the true weight of the person is equal to the apparent weight at the pole. This is at the pole. Okay, at the pole. And at the equator, you notice that the apparent G is smaller. So the weight at the equator is actually smaller than the true weight. Okay, you probably may want to take a snapshot of this one. All right, you may want to pause the video and take a snapshot. Right, so let's move on to the part that we have not covered here. Okay, now we also know that G, the field strength, depends on the distance from the center of the Earth, Gm over R, right? R square. So G is inversely proportional to R square. Okay, so the greater the radius, or rather I should say, the greater the distance from the center of the Earth, the smaller the G. However, we know that actually the radius of the Earth on the equatorial plane is actually slightly more only. It's slightly more, all right, compared to the polar radius. So actually the G at the pole and G at the equator has a small difference due to the radius. So this is the bulging Earth that we are talking about. The radius at the equator is slightly more, okay? Radius at the equator is slightly more than the radius at the pole. Now, for A level, we will not consider a bulging Earth like that. It is bulging at the equator. You see that the equator is bulging out. So we will not consider Earth as a bulging Earth. Instead, for A level, we will consider Earth as a perfect sphere. Perfect sphere. So you write down. So this is what we will consider Earth to be. So this is a perfect sphere. So therefore, the effect of the G due to the difference in R is actually very small. You can make a calculation. Actually, the effect is very small. So there are actually two effects on G. One is the radius, but because at A level we take Earth as a perfect sphere, so everywhere on Earth G is the same, 9.81, right? 9.81 meter per second square. If we were to consider the effect of rotation, then at the equator, G will be smaller by 0.034. Okay, this is the centripetal acceleration, right? As you can see from this formula, okay, G is actually smaller than the true G by 0.034. Okay, where do I get this number? This number is obtained earlier on here. Okay, I got this number from there. Okay, let's move on. Satellites and orbit. Okay, a satellite in orbit has a tangential velocity v, and this v is a unique v. Is unique. In other words, for every orbit of radius r, there is a certain uh, unique velocity v. Okay, so it's a 1-to-1. For certain r, there is a unique v naught. Okay, so suppose you do not supply a value which is exactly v naught, you supply a value which is less, then the body will actually spiral towards Earth. Suppose this red one is Earth. Suppose this is Earth. Then the satellite will actually spiral towards Earth and crash onto Earth. This is a case where v is less than v naught. Okay, so the satellite will just spiral and crash onto Earth. Okay, so this is the circular motion. This is the original circular motion. Or rather, I should say, this is the circle of orbit that we would like the satellite to go around. But if v is less than v naught, then it will crash onto Earth. But what if v is more than v naught? If v is more than v naught, okay, more than v naught, the body will escape the pull of gravity of the Earth. So the satellite will just be lost in outer space. It will spiral outwards and be lost in outer space. So there is a unique tangential velocity that a satellite must have for a certain radius from the center of the Earth. So I'm going to explain this further by showing you this diagram. Okay, look at this satellite. I highlight in yellow. Now, how do I put a satellite there? First, I have to raise the satellite such that it is at a certain r. This is the certain radius r, okay? At a certain radius or certain height from the surface of the Earth. So once I raise it to that level, I have to use a booster rocket to push the satellite tangentially such that it has a unique velocity v. Okay, this v is the v naught that I talked about. A unique velocity v naught. So there is a unique velocity for a certain value of r. So I will highlight this. There is only one speed that the satellite can have if the satellite is to remain in the orbit of radius, let's say r, radius r. So we are going to apply physics here. That is centripetal force. Oops, let me erase this. Centripetal force is provided by the gravitational force. If you are asked to derive Kepler's law, you must state this statement. This statement is important. So you have your gravitational force equals to centripetal force. And then you notice that the weight of the satellite doesn't matter actually because it will be cancelled out, right? So if you pause and look at the mathematics, eventually you get equation 7.6, which is a very important equation because r cubed is proportional to t squared. Okay, r cubed is proportional to t squared because in between you have a constant. Gm divided by 4r squared is a constant. So r cubed is proportional to t squared. This is Kepler's law. Okay, it shows very clearly that for a certain orbit of radius r, there is a unique period. Okay, so therefore we can make this conclusion that according to Kepler's law, for a certain radius r, there's a unique period. Okay, right. Point number two. look at equation 7.6. There is a big M there. Okay, so you are able to find the mass of the bigger body if you know the period and the radius of orbit of the smaller body. So in the case of the sun, if you take sun as the bigger body and the earth as the smaller body going around the sun, as long as you know the period and the orbital radius of the earth, you are able to calculate the mass of the sun. So that's what number 2 means. Number 3, Kepler's law can only be applied if there is only one force acting on the orbital or orbiting body. If there are more than one gravitational force acting on the orbiting body, then Kepler's law is not applicable. And we'll see this in example 8 later. So let's move on to the next part. Okay, example 6. Satellite travel in orbit around the moon at a speed of 1650 meter per second. Determine the mean distance above the surface of the moon, right? So if you are going to show this, then this statement is important, right? You have to write this statement if you are asked to show, right? So basically we are trying to repeat what we have done just now. This is basically equation 7.5. If you look at the previous page, this is basically equation 7.5, except that this time centripetal acceleration, instead of r omega square, I'm using v square over r. Okay, so if you use this formula and substitute the values of the quantity inside the equation, you get the radius of orbit as 1.798 times 10 to the power 6. And if you want the mean distance above the surface of the moon, you are actually calculating the height. So you have to take the radius r minus the radius of the moon. Okay, one is the radius of the moon, the other is the radius of orbit. Okay, so that's how you get the answer. So you pause the video and try to understand the working. Okay, let's move on to work example 7. Why does the moon not fall and hit the earth? Usually this is a 2-mark question. So there are 2 important points here. Number 1, the moon doesn't crash onto earth because it has a horizontal, it has a velocity perpendicular to the gravitational force. Okay, so this is a velocity parallel to the surface of the earth. Another important point you have to tell the examiner is this gravitational force, which is exerted by the earth on the moon, provide the centripetal force that is just sufficient to cause a centripetal acceleration of the moon. So these 2 points are essential. Whenever this question is asked, that you have to give these 2 points. Okay, so I'm afraid that you have to memorize this answer, especially these 2 points. Okay, so you see velocity is perpendicular to the gravitational force, centripetal force is just sufficient. You see, these are the 2 important points. Fortunately, this question came out once, and till now it doesn't come out, but that does not mean that it will not come out, because the question can be modified. Question can be, why does the satellite not fall and hit the earth? Instead of moon, it can be a satellite. Okay, so this question is still relevant. Okay, let's look at work example 8. This is a very special case for a SOHO satellite. This SOHO is actually solar and heliophoric observatory kind of satellite. And this satellite is in between Sun and Earth. And why is it so special? This time there are 2 forces acting on the satellite. One is the force due to the Sun. The other is the force due to the Earth, right? So there are two forces acting, right? So which statement relating to the satellite helps to explain how it is possible for its period to be 1 year? So if you look at A, gravitational field of the sun uh, at the satellite is reduced by the presence of the Earth. Now, this statement is wrong. Let me explain to you why this statement is wrong. Now, G due to the sun is actually equal to G mass of the sun and then divide by R. R is, let's say, suppose we call this R, so it's R squared here. So you notice that this field strength G of the sun depends on the mass of the sun, and it depends on the distance from the center of the sun. So it has nothing to do with the presence of the Earth, okay? So nothing to do with that. It actually is based on this formula, so it is wrong. B, gravitational force of the Earth on the satellite balances the gravitational force of the sun on the satellite. This is wrong because Fs is not equal to Fe. Okay, these two are not equal, right? Let's read it again. Gravitational force of the Earth on the satellite balances the gravitational force of the sun on the satellite. Both heavenly bodies are attracting the satellite, but these two forces are not equal because one force is more than the other to provide a net force. Okay, force due to the sun is more than force due to the Earth, so there is a net force towards the sun. So this is a wrong statement. C, the mass of the satellite is much less than the mass of the Earth. This statement is totally irrelevant because normally when you have a body going around another body, you know the mass of the satellite is not relevant at all. D, the resultant force on the satellite is less than the gravitational force of the Earth exerts on it. This is correct because look at this. You have a net force acting on the satellite. Fs is more than Fe. So this will have to provide the resultant force. So here that is talking about the resultant force. This is F net. F net is less than the gravitational force. This is Fg. Okay, Fg. So obviously Fg is more than F net. Fg is more than F net. Look at this. Oh, I make a mistake. This one is Fs. Sorry for the mistake. Fs. Okay, Fs is more than F net. So Fs is more than F net. Okay, so that's because the Earth exerts a pull to the other side. So there is a net force towards the sun. Okay. So we have covered this. And now we are going to move on to the last concept for the day, geostationary orbit. What is a geostationary orbit? First, what is a geostationary satellite? It is one which is always above a certain point on the Earth as the Earth rotates about its axis. So I'm going to show you a video to illustrate what a geostationary satellite is. So look at this. So as the Earth rotates, the satellite appears above a certain point on the Earth as the Earth rotates. You see, it is always above that particular spot as the Earth rotates. Okay, so that is geostationary satellite. Let's go back to our lecture. Occasionally, the examiner asks you to state what a geostationary orbit is. So you have to modify what you know about geostationary satellite. So you have to say a geostationary orbit is one in which the orbiting satellite is always above a certain point on the Earth as the Earth rotates about its axis. So you just make a slight modification. Next, the characteristic of geostationary satellite. Well, it must have exactly the same period as the Earth because it is always above that certain point on the Earth as the Earth rotates. So the period of geostationary satellite is 24 hours. It must move from west to east. So all these are very important points. Okay, and the satellite is at a fixed height because just now I already told you that there is a unique R for every period. This is because of Kepler's law. R square is proportional to R cube is proportional to T square. That's Kepler's law. All right. So for every orbiting radius, there's a unique period. So we we have seen this before. This is actually just now we call it equation 7.5, right? This equation 7.5, and you must learn to derive this expression because sometimes you may be asked to show the such an expression. Okay, so must learn how to derive this. Number 4, we already spoken about one orbital speed corresponding to a certain radius. Okay, it's unique one to one. So you are able to get the orbital speed using the same expression, equation 7.5. Okay, so equation 7.5 is very important. You better go and learn how to um, um, uh, derive all these. Okay, number 5. Um, geostationary satellite has to move along the equatorial plane. You saw in the video that this geostationary satellite must be in that plane. Okay, so um, last of all, there's a common mistake that I want to highlight. Whenever examiner asks you to define what a geostationary satellite is, there is a tendency for students to give the characteristic of the satellite instead. This is wrong. You should not give the characteristic of the satellite. Instead, you have to quote this one. You have to say it is a satellite uh, which is always above a certain point on the Earth as the Earth rotates about its axis. So this is the answer, or whenever you're asked what a geostationary satellite is, give this answer. Do not give the characteristic. The characteristic is for your own understanding of what a geostationary satellite is. Okay. Um, all right, we have come to the end of the lecture. I would like you to look at the objectives that we presented before you, objectives C and E and J at the start of the lecture. Examine yourself to see how much you understand based on the objectives. Thank you for your kind attention. Bye.